Hello everybody, this is Craig. One of you requested that I give some help with a couple of those standard normal variable problems. And so here I have three of them for you. Um, I like these problems. I actually think they're kind of fun, but I know I'm a math teacher. All right, let's dig in. Let's see, the first one says the time required to complete an assembly of some sort of object, I suppose, is normally distributed with a mean of 21 minutes and a standard deviation of 10 minutes. We are to find the probability that a randomly picked assembly takes between 13 and 22 minutes. Well, the first thing I like to do with these problems is draw a picture. And I start with my standard normal curve, which that's a pretty ugly curve, but that's okay. And let's see, the mean is right in the middle of it. We know 50% of the values are on either side. You did some problems using that fact and one standard deviation, 2 and 3 away. Those were a little bit simpler than the ones I'm going to do tonight. Okay, let's see, what do we know? We know the mean is 21 minutes, and here's the mean right in the middle. The mean is 21 minutes. And it says we want to find the probability. Now, what does that mean in terms of this curve? Probability is the same as the area under this curve. And yes, we're going to be using our standard normal curve areas, those tables that your book always links you to figure some of these things out. All right, we want the probability that a randomly picked assembly takes between 13 and 22 minutes. Well, let's put 13 and 22 minutes on this graph. Let's see if that's 21. 22 must be, I don't know, somewhere like that. We'll call that point 22 minutes. And over here, we'll call this point 13 minutes. And we want the probability or the area that's between those 2 points. Boy, that line is not very straight, is it? Hard to draw with my pen. That's all right. Oh, gee, I'm messing that up good. That's okay. All right. Yes, because what says we want the probability that the assembly takes between 13 and 22 minutes. So that's the area we want to find, the area between 13 and 22. Well, the problem is that we can't just go to our tables with 13 and 22 minutes. We have to convert these values into the standard normal variable form. That's z. And z we know is equal to the x value of interest, the 13 or the 22, minus the population mean divided by the population standard deviation. And we were given all those things. Let's see, standard deviation, yeah, we were given that. Population standard deviation is 10. So let's find the z values that correspond to 13 minutes and 22 minutes. First of all, the 13-minute value. Let's see, that's going to be z is equal to x, 13, minus the mean, 21, over the standard deviation, 10, and that's negative 8 over 10, or negative 0.8. So this 13 minutes corresponds to a z value of negative 0.8. How about the 22 minutes? I'm going to run out of room here. 22 minutes. Let's see, his z value is equal to x, 22, minus the mean, 21, over the standard deviation, and that's equal to 1/10, or 0.1. So the 22-minute value corresponds to a z value of 0.1. All right, now we're looking for this area under the curve. And we can find these probabilities or areas under the curve by going to our standard normal table and looking up these z-values. But here's the tricky part. How does that table work? What it does is it measures from the left edge, somewhere over here, some point over here, and it gives you the probability from that point all the way up to your z-value of interest. So if I look up z of 0.08, and I'll draw another little curve over here and I'll erase it. If I look up z of negative 0.8, it's going to give me this area, everything from the left up to that point. If I look up a z of, let's see, another one we're interested in, a z of 0.1. It starts at the left and it's going to give me the probability of everything from that left edge all the way up to this spot. So we have to think in our minds a little creatively. How would we calculate this area if we were given this area and then that bigger area? Well, the answer is that we can subtract those two. If we are given the area of corresponding to z equals 0.1, which is everything here, all of this to the left of that point, and we subtract everything to the left of the area corresponding to negative 0.8, this little area, we'll be left with the stuff that we're interested in. And that's how we do it. So let's look up these probabilities. How do we write them? Where do I write them? The probability of z being less than or equal to negative 0.8. I'm just looking up negative 0.8 in my table. And what do I find? I find 0.2119. If I look up the probability of z less than or equal to my other value, 0.1, 0.1, where are you? Let's see, 0 is the point 1. Where did you go? Oh, there you are. Okay. It's on z.1 and the gotta find those intersections, right? Sometimes it's a little tricky. But this one I see is equal to 0.5389. Nope, 5398. 0.5398. And now we said we just have to subtract the two to get this area. So this area here, put a big arrow, is equal to 0.5398 minus 0.2119. And if I did my math right, that's 0.3279, or 32.79%. There's the probability that a randomly picked assembly takes between 13 and 22 minutes. It's 32.79%. Very good. What else can I say about this one? Not much. The real trick is, again, we measure in the table. The z-values always are starting on the left and measuring up to the point where we say look up a z-value. So if we looked up this z-value way over here, it would be all the area under the curve up to that point. And so sometimes we've got to subtract one thing from another. And you'll see this again in the next problem. Let's move on. This problem, we have the same assembly, which means our mean was still 21 and our standard deviation is still 10. It says it's unusual for an assembly to take greater than 35 minutes or less than 8. But we want to find the proportion of assemblies that take these unusual, that lie in these proportion of in these, okay, yeah, we want to find the proportion of assemblies that take greater than 35 or less than 8 minutes. Once again, I draw myself a really bad picture. We still have the mean of 21. We still have the SD, the standard deviation, population standard deviation of 10. And what are we looking for? 8 minutes. He's got to be way over, pretty low down here. So it said we want them less than 0.8. So really, we're looking for this little piece, aren't we? That's at 8 minutes. And over on this end, it said we want guys that are greater than 35 minutes. Doesn't matter that I'm not drawing these exact. No, not really. Okay, we're going to take the same tact. We know we're going to have to get z-values for these 2 points, so let's just start with that. Let's start with the 8-minute piece. And the z-value is, oh, wait a second. Hold your horses. Come on, work. There we go. All that to move him over there. All right. Z is equal to, well, we'll write it out again. X minus the population mean divided by the population standard deviation. Okay, we're at 8 minutes minus 21 is the mean. Over 10 is a standard deviation. And let's see, get back on the right page. Difference here is 13, so that's negative 13 over 10, which is negative 1.3. All right, that's the z-value corresponding with 8 minutes. Negative 1.3. And recall, what are z-values? Well, those are standard deviations away from the mean. So, 8 minutes is 1.3 standard deviations away from the mean of 21. How about this 35 guy? 35 minutes, where's he at? Well, he's at z of 35 minus 21 over 10. He's a little further away. He's at 14 over 10, or 1.4 standard deviations, a z-value of 1.4. All right, now how are we going to do the math? Recall, when we look up z-values in our table to find areas, it's always the area from the very left-hand side where things have just gone down to nothingness over here. And it's the area from there filling in all the space up to whatever your point of interest is. So, let's see, how are we going to get this little area and this little area? Well, the 8-minute is going to be easy, isn't it? Because when we look up the z-value of negative 1.3, it'll be exactly the area that we want. Let's do that one. That's the simple one. Probability of z being less than or equal to negative 1.3. I'm going to look up negative 1.3 in my textbook, and it says it's 0.0968. 0.0968. All right, now this one's a little tricky. We can't just look up z of 1.4 or it's going to be a really big value. You know, it's covering a lot of space here. But what we're going to do is rely on the symmetry of this curve. What if we took this 1.4 and thought of it as negative 1.4? Actually, it's a little bit lower than that 1.3 value. It's in here. But because of symmetry, we can look at z equals negative 1.4, and it's the same as looking at z equals 1.4. we can, here we have z equals 1.4, and there's an area. Well, we can just as well look at z equals negative 1.4, and we get the same area. Area 1, area 2, and what we know is that area 1 is equal to area 2. So again, we're making use of symmetry. Why is that important? It's because we want this little area. We want this little area, and we know it's the same area as this one. But if we look up negative 1.4, we'll be given this little area, which is the same as that little area, which is what we want. Then we're simply going to add this area, which we've now calculated, is equal to what? 0. Oh, sorry. 0. Go away, come back. 0.0968. All right, so let's look up the other one. We're going to look up the probability of z being less than or equal to negative 1.4. And when I look up negative 1.4, I get 0.0808. Now to get these areas together, and again, yeah, this one here, 0.0808. I can just simply add those two together. And let's see, we'll do that right here. 0.0968 plus 0.0808. And checking my notes. Sum those and you get 0.1776. Convert that to a percent by moving 2 decimal places to the right. That's 17.76%. All right. That's what those little areas represent. 17.76% probability. It's 17.76% of the area under the curve. How much area of the curve is this big white spot in the middle then? Well, it's simply the difference between 1, which is the area under the whole curve, and subtracting out those little areas, it would be, what, 0.8, not 83, 0.8, 82 point something, right? Yeah. All right. Let's move on to our third and final problem. This one's a little bit different. A random variable, call it x, is normally distributed. It's known that the probability of x being greater than 181 is 3%. We want to find the population mean if the standard deviation is 8. And then we're going to turn it around and find the population standard deviation if the population mean is 159. Oh boy. Start the same way I start every one of these. This is so helpful to me. Hey, my curves are getting better. All right, we've got a mean. And what is it in the first problem? We don't know. It's what we're looking for. A population mean. If the standard deviation, population standard deviation is 8, good. And we know something. We know the probability of this variable, random variable x, being greater than 181 is 0.03. Well, let's see, a probability of 0.03 is pretty small. So if we're looking at something being greater than a number, this point will represent my number 181, my variable x. And here's my little probability, 0.03. I knew not to draw this horribly not straight line over here because no, the probability of this thing being greater than 181 is really small, 0.03. So that's how I knew it was way up here. All right, what are we going to do? Well, we're going to use our relationship, our definition of the standard normal variable, z being x minus standard, I'm sorry, population mean over the population standard deviation. Let's fill in what we know. We don't know z yet, do we? Nope, we don't. But we're going to find him. Let's see, x, yeah, we're looking at the point where it's 181. And there's the population mean. That's the guy we're looking for. And we do know the population standard deviation. So we got two variables here. If we find one more, we'll be able to solve for the last. We got to find the z value, and we have enough information to do that. Okay, so we know that the probability of x being greater than 181 is equal to 0.3. Well, this is one of those problems where I'm going to rely on symmetry. I know if this area is 0.03, this big area is 0.97. So I can just turn this around and say, okay, the probability of x being greater than 181 is 0.03. The probability of x being less than or equal to 181, that's all this white space here, is equal to 0.97. Ah. So that's good. I mean, that's good to know because now I know when I look up values in a z table, they go from the left over to this point, and I know what this area is. This area is equal to 97% or 0.97. And so now this time I'm going to use my standard normal curve areas table backwards. I'm not taking a z value to it and finding an area. I know the area. I want to know the z value that corresponds to 181. That's what I'm looking for. So if I go to my table and I'm looking for 0.97, let's see, 0.97 only appears in one spot in this table. I forget where it was. There it is. I find the value of 0.9699, which is very close to 0.97. That's the value they want us to use, at 1.88. This value corresponds to z of being 1.88. Okay, so now I have the missing piece of information. Messing things up here that I need. I can now put 1.88 in for z. So let's see. Now it's just a math problem. 1.88 equals 181 minus our one variable. Okay, I'm going to multiply both sides by 8, which will cancel out that 8. I'll have 8 times 1.88. Right? If I multiply both sides by 8, this 8 cancels. And now I'm left with 181 minus the population mean. Now I'm going to use my addition property of equality. I'm also teaching algebra face-to-face this semester, and we've been using that guy a lot for those beginning algebra students. I know I can isolate my population mean by subtracting 181 from each side. So let's see, I'm just going to leave it not multiplied together yet. Subtract 181. And when I subtract 181 from this side, it goes away. Ooh, we're left with a negative population mean. Let's do the math now. Where's my calculator? Over here where you can't see it. Oh, look at that fancy Windows 10 calculator. I don't like it. But if I do 1.88 times 8. I get 15.04. 15.04 minus 181 equals negative population mean. And now I gotta do math one more time. Oh, I didn't mean to start word, go away. Oh boy. Come back. There we go. 15.04 minus 181 is equal to negative 160. Oh, it goes away as soon as I click. Did I write it down? Yep. Negative 165.96 is equal to negative population mean. Multiply both sides by negative 1, and we have the population mean. Here's our answer. Let's see, they wanted us to round to, I think, a single decimal place, which means my answer would be 166.0. There's my population mean. It's 166.0. Okay, the last part of this problem is just turning things around. It's the same problem. We still have, well, it's a little bit different. Should we erase and start over? Yeah, let's clear the board. Pause now. It's gonna go. 3, 2, 1, boom. Let's draw a picture again. And this time we have a known population mean. Population mean is 159. And this time we don't know the standard deviation. That's what we're looking for. Okay, we still had this value of 181 out here. 181. And it still corresponds with a z-value of, I don't remember. What was it? Oh, I killed it. Let's see. Checking my notes. 1.88. Yes, I heard you all yelling. 1.88. Okay. Gosh, we don't have much left to do on this one. We simply need to use our definition of the standard normal variable and plug in and do the math. So z 1.88 is equal to our value of x 181 minus the population mean 159 over our unknown. All right, I know if we cross multiply, it's the same as I can just flip these guys around here. That denominator and this numerator, just flip places. That's that over 1.88 and 181 minus 159. I didn't write that one down. Let's pull up my calculator. 181 minus 159 is equal to 22. 22 over 1.88, which I did write that one down. That's 11.70. Okay. Hey, there's my answer. That was simpler, wasn't it? Yeah, because we didn't have to repeat all the work we did here. Looking for, knowing that that's 0.03 and being able to recognize that that makes this. If he's 0.03, this is 0.97, and then we could use our standard normal curve area table and look up 0.97 and find the z value that corresponded to that, which was 1.88. Yep. And then work our problem. All right, folks. Oh, 29 minutes and 53 seconds. There's a good half-hour video for you. I hope this helps. Keep asking questions, guys. We're getting through this stuff, and I think I'm seeing a light at the end of the tunnel. And yeah, things are not going to get harder anymore. This stuff, yeah, this was a little tricky, but I think you're going to like the rest of the course. It kind of makes a little bit more sense. Some of that probability stuff, that was a little bit bizarre, wasn't it? All right, guys. Talk to you soon. Bye bye.